I bought one of those cold packs that you get. You just squeeze it and then something pops inside and you shake it and it gets really cold. And so I wanted to know what was inside. I cut it open and I found that there were these little pellets, which is calcium ammonium nitrate, which is a salt, and a little bag of water. So when you pop it, you're rupturing the water bag. And then when you shake it, you're mixing it. And the salt is dissolving in the water. Well, I thought, I want to see how cold that's going to get. And so I masked how much calcium ammonium nitrate I had. And I started with 21.1 degrees Celsius water, 50 milliliters of it in 2 styrofoam cups, which I call my calorimeter. And then I added the salt, put on the lid, put my thermometer in. Careful, it's sharp. You don't want to puncture those styrofoam cups. And then I shook it to dissolve the salt in that water, which isn't easy to do with one hand. And my goal was to see how cold will that solution get. The coldest I could get it to was 3.8 degrees Celsius. So at 21.1 degrees Celsius, the water lost energy. Where did it go? And the answer is it went into the salt dissolving. So I'm starting with the idea that there is no heat lost or gained. That the heat that has been gained by the salt that caused the water to become colder was lost by the water. So I'm using blue to indicate heat has been absorbed. And I'm using red to indicate something gave off heat. When heat is absorbed, we say that is an endothermic process or an endothermic reaction. And when heat is lost, we say that is exothermic. That chemical reaction or that physical process was exothermic. So I had my coffee cup calorimeter, 2 coffee cups, styrofoam cups that are nestled, and 50 mils of water. And I poured my salt into that. The salt that is in those cold forming packs is calcium ammonium nitrate, which is a fertilizer. So it's a nitrate salt, a soluble salt that has 2 cations, calcium ion and ammonium ion. My goal was to find how much energy is absorbed by that salt on a per gram basis. I wanted to find the heat of dissolution, dissolving, for this salt. So I had my coffee cup calorimeter and a lid with 50 mils of water in it. And on a conservation of energy idea, I'm saying that the heat that is absorbed by the salt is equal to in magnitude, but opposite in sign, of the heat that is lost by the water. So I subtract the heat transferred of the salt, Q salt, from both sides, and I have negative Q salt equals Q water, and I'm making the assumption that the heat lost by the water is going to be approximately the same heat lost by the solution, and that is a typical assumption in this kind of problem. For the water, I'm saying heat transferred Q equals MC delta T. I started with 50 mils of water that I measured out in a graduated cylinder, and I know that the density of water at 4 degrees Celsius is 1.00 grams per milliliter, and that's a good approximation for what we have now. However, I've just written that 50 milliliters times its density equals 50 milliliters, and the result should be 50 grams. The specific heat of water is 4.184 joules per gram degree C, which is the same as 1.00 calories per gram degree C. In this situation, I'm going to solve the answer in joules, but those are values that you should know for pure water as a liquid. The change in temperature is final minus initial. I started with warm water. It was 21.1 degrees Celsius. And as I added the salt and the salt dissolved, it got colder. So the final temperature is less than the initial temperature, which is typical for an endothermic process. In an endothermic process, heat is absorbed. So my mass was 50.0 grams. The specific heat for water as a liquid is 4.184 joules per gram degree C, which is a value you should memorize. And the change in temperature for the water that became a solution was negative 17.3 degrees Celsius. So I come up with a value to several sig figs that's only good to 3 sig figs. And so the heat that was lost by the water was negative 3,620 joules. For an exothermic process, the sign is negative, always. Where did that energy that was lost go? It went to the salt. So how much energy did the salt absorb? 3,620 joules. Now my goal is to find the enthalpy of dissolution, and the symbol for enthalpy is H. It is related to the heat transferred, but it's the heat transferred on a per gram basis. And so I'm going to divide the heat transferred to the salt dissolving by the grams of salt that were dissolved. And we come up with a value that is good to 3 sig figs, which is 116 joules per gram. Now this is a value that we've determined empirically in the lab, and we could compare it to a value that somebody else has determined in the lab in a table and look for a percent error. But I have answered my question. What is the enthalpy of dissolution? It's 116 joules per gram. And because that's a positive value, that indicates that this was an endothermic process. So I just opened that bag of water that was inside the package, and I thought, how many grams of water are in there? And it was 45.0 grams. So the question is, how cold would that heat pack have gotten? I had 50 grams of water, but the actual grams of water were 45 grams. So let's say that the initial temperature was room temperature, 25.0 grams degrees Celsius. And the question is, what would the final temperature be? Well, if I know delta T, I can solve for T final. The mass of the water that was actually in the cold pack was 45.0 grams. The specific heat of water hasn't changed. And we're making the assumption that that is the same specific heat of the solution, which is a good assumption. The mass of the salt the mass of the salt that I'm using is the same mass as before, 31.2 grams, because that was the mass of the salt in that container. The enthalpy for that salt dissolving is the enthalpy that I just solved in my previous experiment, 116 joules per gram. The change in heat is the mass times its enthalpy. So for the salt, I have a mass and enthalpy. For the heat transfer for the water, it's MC delta T. So I'm starting with a conservation of energy argument that the heat transfer to the salt came from the water. And I'm going to substitute the equations for heat transfer. For the salt, that's M delta H. And for the water, which becomes a solution, it's MC delta T. My goal is to solve for delta T. And once I know delta T and the T initial, I can get the T final. You might be thinking, why delta H for the salt and MC delta T for the solution? And the answer is, I can only use the equation that has delta T if I have a change in temperature I can measure. And I can't really measure the change in temperature for the salt. At this point, it's just algebra, but I definitely recommend for this chapter that you practice the algebra for all the problems because it can be a little bit tricky. And as you practice, you build that skill. So I've solved for delta T, and delta T is the temperature went down 19.2 degrees Celsius, but that isn't the answer because the question was, what is the final temperature? We started at 25 degrees Celsius, so T final minus T initial, that's what equals delta T. Because the change in temperature is good to the 10th place and the initial temperature was good to the 10th place, the change T final is good to the 10th place, and the answer is 5.8 degrees Celsius is the final temperature in theory for this cold pack.